Pachek.
I'm Danny.
And we're Pachek and Pasakov, kind of a cool alliteration. And we did the home audio system.
All right, so the presentation structure for today, we're going to go over the high-level design, kind of show what there is in the scope of this. Next, we're going to touch on the graphic equalizer, show all of the different parts. One cool thing we implemented from the last presentation is a PCB design, as Pachek has in his hand. So we're going to go over all the good stuff there. Next, we're going to check out the spectrogram, and then the Class D amplifier.
So I guess when we first did our first presentation, we had like a bunch of stretch goals. Turns out we weren't able to do any of them other than the PCBs, which were a very interesting thing to learn. So right here we have 4 stages of 4th order multiple feedback bandpass filters, as we first discussed in the first presentation, with each stage having an inverting amplifier at the end to apply a boost or cut to each stage, as well as embedded within the actual block, a buffer in the beginning, which we'll touch on a little bit later. That goes into a summing amplifier, which then goes into the Class D. And then all of these are then sampled by the Arduino microcontroller, and then we have our spectrogram on the display.
All right, so first thing we're going to do is the graphic equalizer. We're going to check out the frequency partitions. So rather than 3 EQ bands, we decided to do 4. 1 for the low, 1 for the high, and we decided to do 2 for the mids.
So the idea being there's 5 here, but one of our PCBs broke, and then we wanted to keep one of the other ones for ourselves, and 4 is symmetrical. So we ended up doing 4 instead of the 5. This is our filter topology per bandpass filter. So as I mentioned before, it's a 4th order Buttersworth multiple feedback bandpass filter. What we found was that what makes it Buttersworth is basically how you compute the center frequencies versus the first stage and the second stage. So if you have the same center frequency and the same bandwidth for both of these multiple feedback filters, then it's going to be Buttersworth. If you spread them out a little bit and then you reduce the bandwidth, then it's going to be like a Chebyshev. As we mentioned before, it's a 4th order filter, which means that it's going to be in phase at the end, allowing for us not to have to compensate for any phase or have to apply any phase shifts at the end. It's 4th order, meaning that it's going to have a 24 dB per octave roll off after you pass that cutoff frequency, and it's simpler to implement than the variable bandpass tuner that we originally had. We had the voltage follower / the buffer at the beginning to reduce the reflection coefficients, and we saw that improved the S parameters that we were measuring. And then we have the inverting amp at the end to kind of actually boost that. Let's see. The PCB filter design, I will admit this took way longer than I would like to admit, but it was a pretty fun learning experience. So I guess I want to pass it. It's pretty sturdy, so you can kind of just pass it around. So we made a PCB. Right here we have our quad op amps, the LM or
324.
Yeah, the 324s, as well as these 2 resistors right here, and then the header pins, and then the things that actually connect to the potentiometers here. Right here is the very cool idea, I think, and it's basically a socket that's socketing a ZIF socket. This is right here is a ZIF socket where you're able to put in all your capacitor components and all your resistor components and make any filter you want. So if you want a high pass filter, you just change the order of the capacitors, resistors. If you want a low pass filter, etc. Or if you want the bandpass filter, as we're doing today, it's in the current configuration as you see now. To actually do this PCB design, we actually ended up using a 74 series or the 74 LS series chip to use the schematic because it used the same dip switch. But yeah, this was a fun build. One thing to note about the PCBs is this is my first actual PCB that I made, and then surprisingly worked first try. I have no idea how. But it's pretty cool. Here's a couple more photos of I guess some of the more preliminary designs before we got to this stage right here. So here we have the slider that's going to control the boost, and then the cut right here. So being able to tune all of them, since each bandpass filter has a little bit of a different power dissipation. as well as the graphic equalizer circuit in its total, as you see, 4 stages in the semming amp, as well as some other. This is the current implementation. One thing to note is we originally had this all on breadboards, and this is when we kind of like showed it to Sarker and then like validated it. And this is like when we started taking all our validation for the report. And then we started moving it to this area where all the filters were still working great. And then we designed some like 3D printed parts around sliders. And then we have the validation for, we could see all the filters summed out at the output.
All right. So now we're going to cover the Class D amplifier. This is going to be the amplification stage. So going over a high-level design, we're going to have a comparator. That is going to compare the audio input with a triangle wave. Now we went ahead and made our own triangle wave generator. It uses a non-inverting Schmitt trigger mixed with a ramp generator. Oh, and then from there, it's going to output a PWM signal. That PWM signal is going to have a high side, and then it's going to get split off into a low side as well. Those two are going to go into 2 NMOS MOSFETs that will then go into the amplification stage. After the amplification stage, they will be recombined going through a low-pass filter, and a replica of the original audio signal will be output to a speaker or headphones. All right, so here is the LT Spice schematic of the Class D amplifier. We tried running it as a whole. It took over an hour and did not work. So we validated the first subsystem on its own, but the rest wouldn't work in Spice. Next. All right, so here is the Class D amp. We've got, so the triangle wave generator has a voltage potentiometer to control, it controls basically the voltage of the triangle wave, the amplitude. And the next is to control the frequency bandwidth of the triangle wave. So this is just a validation of the triangle wave generator that it works. Now we have the validation of the comparator stage. So basically the blue is a frequency sweep on the input of the comparator, and the orange is going to be the output of the comparator. And as you can see, it's a pulse width modulated signal. Okay, so now we have the inverter output. So interesting configuration. In order to invert the signal, we used a BJT transistor as an inverter, and we tried sending the original signal into the high side, but the MOSFET wouldn't turn on. Now that was due to the MOSFET's gate capacitance. So in order to combat that, we inverted the high side signal and inverted it again. So kind of a double inversion to boost enough to add current to the circuit, so both the MOSFETs would be able to turn on and amplify accordingly. And now this is the output of the amplification stage. And now this is the output versus the input of the entire Class D section alone. So the blue is another frequency sweep of the Class D. So basically that would be the audio signal. The reason we do a frequency sweep is to kind of simulate all frequencies, similar to how music would be. And you can see the orange is the output. Now we were getting a pretty substantial gain, so that was pretty pleasant. The only issue is on the low frequencies, we were getting some clipping. We weren't able to figure out why, but it didn't cause too much of an actual issue. And now this is a demo with real music. So we plugged a real audio file in and got the orange, well, the orange is the original, and then the blue is the output gain. So we were getting about a gain of 2 for the amplification stage, which is pretty good. We were happy about that.
So I guess before we go to the spectrogram, yeah. I mean, one interesting part about the whole design, and Danny definitely touched on it, is like one of the biggest issues while designing this Class D was like RC charging. Like it was a huge issue, right? All these like active components, like these MOSFETs or like these BJTs or whatever it may be, all have like this gate capacitance, and we found that like it will not the whatever component it may be, it will not fully turn on even if it like passes the threshold level, whether that be the gate source threshold level or whatever current threshold level it needs to be at the base. It won't turn on fully or as fast unless the entire gate capacitance is fully charged. So the idea being with these transistors, that's also applying like a current gain that's able to apply more current to that gate capacitance, because like current is dq/dt, like the changing current over time. So like more current, you can charge the gate capacitance faster, which gets rid of that RC charging, which also kind of like had a low pass effect on the circuit. So here's the spectrogram. This is like a display that we used in the initial design as well. This one takes SPI commands in addition to a clock signal. And as we see right here, we have our two filters boosted right here, so the base and the mids are boosted. And then here we have the highs boosted. And then here's some of the code for it. So interestingly enough, the library that we were using to interface with this like display did not have bars whatsoever. So right above this is just like a bunch of code for like defining bars and like how to make a bar. So we hear like no bar, bar 1, bar 2, all the way to like bar 7 to like define how tall the bar is going to be. So in the setup, we just like declare our pins. These are the pins that are going to be reading from the actual filters, and then add the character, like the actual bars that we had defined earlier up. That way we can actually display them later on. And then the actual like main meat of it in the loop. Basically, we're just sampling each filter and then taking the max voltage of each filter, and then we're remapping that into the range of 0 to 8, right? So no matter what the max value, because these analog pins could sample all the way up to 1023, we would remap that all the way from 0 to 8. That way we'd be able to display a bar from 0 to 8 using the map function in Arduino, and then we would just display that through the LCD display.
All right, there are sources, that's the end, but a couple, let me go back just to get to the lighting. All right, one other thing I wanted to just mention, if we could go back and work on a couple of things. So one thing we tried incorporating a couple nights ago was Bluetooth, that we could send a Bluetooth signal, like Bluetooth audio as the input. That did not work because the Bluetooth module we were dealing with couldn't transfer enough data fast enough. So that just was a dead end. But that was something definitely cool we wanted to try. Another thing we wanted to try was an impedance matching transformer to be able to like output to
Any type of speaker
practically.
So our current LC filter was like designed around the current speakers that we were using, and the AmpLab speakers that we were kind of playing around with. But like in theory, with an impedance matching transformer, you could have your circuit work with any speaker and still have maximum power transfer. The other thing that we were working on, which is what we originally presented as well, was the variable bandpass tuner. Sadly, we weren't able to get it working on breadboard, so we decided not to go through with it for the final implementation. But this is still something that's deep in my heart, so I still definitely will be working on this EVT later. So,
all right, thank you guys.
Any questions?
Thank you. Any questions? All right, thank you. Thank you.